So I think with us is Dr. Bhavna Sani also. I think she has joined. I welcome Dr. Bhavna Sani on board. She's my wonderful colleague of mine, and we have worked together for more than a decade or so. Once she took over teaching research methodology at GMC Jammu, I thought I should give way to her because she does the job much better than I do. So let me confess, I may be little rusty in my speech, but certainly I'm not rusty in my mind. I may have grown a little old, but my senses are all right. So I'd like to have you on board for almost an hour. You will forgive me for if I take a few minutes less or more. And while actually preparing this presentation, over the last 30 years, what I have felt about p-value, I would like to share in a minute or two. At some point of time in GMC Jammu, I was the most sought after person, and researchers of all hues, undergraduate, postgraduate faculty, usually would approach me with one particular question. And the question was, without even saying sometimes hello and good morning, sir, p-value chahiye. Now this question actually is one of the most common questions which I have encountered throughout my life. It was a formidable task telling those people, including faculty, that p-value is not something which I would put my hands in one of my pockets and give it to you. To understand p-value, to apply p-value requires some sort of understanding. In case you want to stop me somewhere, I have no issue. You stop me and tell me whether I'm going fast or slow or whatever it is. Okay?
Yes, sir, sure.
Okay. So while I was thinking of what caption I should give to my talk today, you had given one caption, which was p-value and errors or something like that. I thought it would be much better if you think of a p-value, please mind the gap. Some of you must be aware this phrase, mind the gap, has come from the tube, underground tube in UK, and it was adopted by the metro. So I thought we are going to have a metro ride today from 7:30 to 8:30, and metro usually run in time. The only difference between this ride and the actual metro ride is that the दरवाजे मेट्रो के एक तरफ खुलते हैं, चाहे दाएं चाहे बाएं, रियल मेट्रो के. यहां मेरी इंटेंट रहेगी कि दोनों तरफ के दरवाजे खुले, आपके भी और मेरे भी. If I'm able to do that, I think I would be able to do justice to my talk. Right? So let me continue. Let me give you a situation. Can you see my slide?
Yes, sir, it's visible.
Okay. So let me give you a situation. And the situation is about two friends, one surgeon and one physician. And they usually went to play golf on Saturday afternoons. And sometime it was decided that one of them is going to pay for drinks. So they said, what is the mechanism we should adopt for paying for the drinks? They said, okay, we'll toss a coin. If it comes heads, if both come heads, obviously you are going to retoss. If both come tail, obviously they are going to retoss. Until one of them gets head or tail. One who gets head pays for the drink. So on the first three occasions, the physician tossed the coin And we believe that this was an unbiased kind, unlike the one which Biru possessed. Jaya possessed in Sholay. Sholay, he had the kind which had both sides as head. Right? So we believe that this kind, which the physician had, was a fair kind. So 3 times it happened that the physician tossed tails and the surgeon had to pay very willingly, without any making any fuss. The surgeon bought the beverages. On the fourth successive occasion, the surgeon made the expenses, but he was little less willingly made it. Okay. Same happened after fifth. And after fifth, then he went home to his wife. The surgeon muttered that I'm sure the physician is overboard. There doesn't seem to be any hanky-panky with the physician, but there seems to be something rather uncanny in his tail-tossing ability. However, the surgeon's wife was able to reassure her husband and said, it is obviously just bad luck on your part. It just may be entirely due to chance. Just ignore it. The 6th week, surgeon tossed the unlucky head again, and he had to pay. After the 7th came, the surgeon's wife was faced with a very belligerent husband. She agreed that enough was enough. Even though there was no proof that the physician was employing a trick, it was very suspicious nonetheless. And she muttered, the line must be drawn somewhere. She said, if it happens again, you must play golf with someone else. I hope you got the entire scenario. It's clear to everybody?
Yes, sir. Yes, sir.
Yes. Okay. Somebody else can also respond. You don't have to respond for everybody else. Okay. Now, this story has some statistical marvels, which we are going to learn and which will pave the way for our understanding of the p-value. So the first moral is any set of results, whether they are associations, whether they are differences, any investigation, any experiment, as the surgeon's wife pointed out, could be entirely due to chance. And I must add that statistics, it said, it doesn't prove anything. The only way is to refute something. And this would become clear a little later. Statisticians also assume that chance is the only factor initially. But if we go ahead, as in the story, a time comes when it almost becomes very important that the line must be drawn somewhere. Otherwise, no conclusions can be drawn and no action can be taken. No decision can be taken. Chance would always be there to blame, but the time comes when the evidence is such that it is more realistic to assume some other factor. Let's go ahead. Now, gone are the days, which is a pre-antibiotic area, or when the antibiotics were being discovered. There were many instances where when you gave an agent, there was a dramatic recovery. If you remember, if some of you would have read, insulin was like a death sentence. A 5-year survival even less than many cancers. But once insulin came, there was a dramatic recovery. And there was absolutely no need to go for an experimental trial. Everybody believed the difference was such big. Similarly, it happened with streptomycin. We are going to talk about streptomycin example today also and maybe later. Tubercular meningitis in 1944 was a fatal.
Excuse me, sir. You're not audible.
Now you have a plethora of drugs. You have any number of drugs for hypertension. You have any number of drugs for diabetes. You have any number of drugs for chronic degenerative diseases. And the margin of difference sometimes is very less. Now, this margin of difference doesn't allow the common sense to make a decision one way or the other. Whether to accept that this is better than the older one, or it is worse than, or it is sin. So now we have to make very careful examination of the data. And when I say careful examination of the data means that design has to be good, the analysis has to be good. If you look at the law is also practiced similarly. The law states that everybody is innocent until proved guilty. Now, this idea is rather known as what we call as a null hypothesis. Null hypothesis is that a difference between the two arms, two treatment, two intervention is no more there. That means difference is zero, or the intervention A and intervention B
Excuse me, sir. You're not audible.
is that there is a difference between A and B. Can't put, what we do actually is we refute an hypothesis, because a refutation becomes much easier than proving something, proving a theory or proving a hypothesis. I'll give you an example. And the most famous example which is given is of white swan. Some of you may know that there's understanding that all swans are white. Now, if you have to prove this, that all swans are white, what an investigator has to do? He has to examine the last swan in the world, wherever it is, to prove that all swans are white. And till 15th centuries, 1500 AD, until a black swan was seen in Australia. Now, once you saw a black swan, your hypothesis is refuted. When you say all swans are white, you find some other colored swan and you refute your hypothesis. But to prove it is exceedingly difficult. So that is why the hypothetical deductive approach, I would not use these words, the general way of looking at is that you make an hypothesis and you say that initially there is no difference. If there is any difference, it could be due to chance. But you go on and collect data and try to refute that null hypothesis is not true, that there is a difference. And that is what the class is all about. I hope things are clear.
Yes, sir, it's clear, sir.
Okay, fine. Anytime you find a little problem, just stop me. I can repeat it, okay?
Sure, sir.
Okay, now the big question is, the line must be drawn somewhere. A time comes when the evidence is such that we must stop supporting the null hypothesis and give our allegiance to the alternate hypothesis. When this point is reached, what we do? We conclude that we reject the null hypothesis, right? We reject the null hypothesis, and then we accept the alternative hypothesis, right? Okay, where is that? Just a minute. Okay, now let me give you a situation. You had one situation where there was a surgeon and there was a physician, and who were doing some tasks, activity to pay for the beverages. Let me give you another situation. Dr. DK, I thought I'll take it upon myself, is conducting a drug trial to decide whether a particular type of pneumonia responds better to injections of long-acting penicillin or crystal penicillin. So in this situation, what would be your null hypothesis? Your null hypothesis would be, the null hypothesis is going to be that the difference, whatever difference you would observe, is due to chance variation. The alternative would be that it is a real difference. Now, look at the figure D. And you see 4 points. In the middle, there is a line which says there is no difference. This is what the null hypothesis is. Then there's a point which is A, which is close to null hypothesis. Then there is point B on the right side. And then there is point C on left side. On one side, it is long-acting penicillin is the best. On the other side, this crystalline penicillin is the best. Okay? So let's make sense of this figure. Now, what would be your decision? If it is B, what would you do? B is quite far away. You would reject. I'll further clarify why you are going to do. With C, you would reject. What do you do with A? It's problematic. But as you will understand later, I'll say we'll also accept the null hypothesis here. We see why. Now look at a situation where D is added. D is here, right? No, there is no difference, which is the middle line, vertical line. B and C, I said that you will reject the null hypothesis. A, I said you will again accept the null hypothesis. D, a little tricky. Now, who is going to decide? Remember, the surgeon's wife said the line has to be drawn somewhere. Now, who's going to draw that line? Let me tell you, it is the investigator who draws that line. And we in statistics have some rules, though arbitrary, to draw those lines. If your results are within that, you accept the null hypothesis. If are beyond that, then you reject the null hypothesis. I'll explain it in the next slide. Now, this is what the surgeon's wife said in the story. It says, the line must be drawn somewhere. The actual line is this. The actual line is this, which is the, I'm sorry, my pen is not working. You could see that the arrow, which is at the significance level. So this is a line which statistician has advocated. But there is not a very, very strong scientific basis on that. You will come to know about it better once we see the next slide. Look at this. Sorry. I think my presentation has gone a bit wrong. Let me do something. You could see two things in this slide. One of them is the two tails. I said there is a line, which is the middle one, which is of no difference. And there are two tails. And the line of significance is on both the tails. So it could be both ways. Sometimes long-acting penicillin could be better than the crystalline, or sometimes crystalline could be better than long-acting. And the level which is drawn is 0.05. If you add up 0.025 and 0.025, it becomes 0.05. And that becomes your level of confidence in your results. And that is what is actually being told upfront when you conduct your study. Okay, let me tell you. The tails could also be 0.05. The tails could also be 0.05. 0.05 means 0.05 plus 0.05 on either side would become 0.01. I think it is an extra zero which is there. Now, there could be two yardsticks. One is 0.05. That means upfront, you are accepting that 5 in 100 times. 0.05 is 5%, which also translates into 5 in 100 times. 5 in 100 times, you may make a wrong conclusion. That you may reject the null hypothesis when it is true. That means you say that there is no difference when actually there is a difference. And at 0.01 level, you're taking this confidence to further narrowing it to 0.01. That is, you are willing to make a wrong decision 1 in 100 times. So which would give you more confidence? 5 in 100 or 1 in 100? Where you would be more comfortable? Anybody can reply? Hello?
5 in 100.
Pardon?
5 in 100.
5 in 100 is 1 in 20. 1 in 100 is less than that. You are giving chance and explanation 5 in 100 times. And you are giving chance and explanation 1 in 100. So which one do you think is more confident you are with? If you take the level to 0.01, you make a wrong conclusion 1 in 100 times rather than making 1 in 20 times. 5 in 100 would be 1 in 20, right? And there are other levels which are used. But generally, you find in journals, you find 0.05 and a star on top of it as a superscript. That means it's significant. Then you say 0.01 and 2 stars. That means it's highly significant. Then sometimes it is less than 0.001, 1 in 1000, which is very highly significant. But we generally go with, whenever we decide, we go with 0.05 as conventional level of significance. Okay. Now, once you have understood this, you have understood something that you are the one, or we are the one as investigators, who are going to choose that level of significance. So then, what is P? Now, let me give you the definition. And you must be very careful in listening to what I'm saying. I'll make it clear in the next slides. P is defined as the probability. Probability means something would happen over something would not happen. Defined as the probability of obtaining a result equal to or more extreme than the one obtained. I'll explain it. Just remember, it's the probability of obtaining a result equal to or more extreme than the one obtained if the null hypothesis was true. So if there was no difference, you said that there is a null hypothesis and you're going to refute it by collecting some data. So when you collect data, you'll get some result. And then you'll see which side of confidence it is. The smaller the P, the less evidence to support the null hypothesis and great evidence to support the alternate hypothesis. Let me give you. I'll further clarify in the next slide. So 0.01 is more stringent than 0.05. Agreed? 0.05, I once again repeat, is the arbitrary cutoff. So what about 0.04? That becomes 1 in 25. If it is at the level 0.04, you will still consider it as significant. You reject the null hypothesis and you say that there is a difference. What would happen if it is 0.06? 0.06 would be 1 in 16. And unfortunately, you say you do not have enough evidence to reject the null hypothesis. So you accept the null hypothesis in this case. Now, the moot point which I want to make here is that you have a level which is 0.05. If you have set the level of confidence at 0.01, predetermined beforehand, that you will only accept your results if it comes at 0.01. Then even if it comes at 0.05, it should have made no importance to your decision. But if you have made conventional, which is 0.05, so anything lower than that, 0.04, 0.03, 0.02, 0.01 becomes statistically significant. I'll come to what is the difference between this statistical significance and the clinical significance. Okay. Now let us do a small exercise. The small exercise is Dr. D.K. wonders whether more boys or girls get intestinal perforation as a complication of typhoid. I don't know how many of you have read typhoid, but generally believe that more boys get intestinal perforation than more females. But this is an hypothesis, whether more boys or girls get intestinal perforation as a complication. So the observation he makes, out of the 7 cases he sees, there are 6 were males and 1 were female. Now you could imagine this 6 male and 1 female could be just be chance finding. Let's say you take another sample of 7 cases and you imagine and you observe 5 and 2. Another sample you may say 4 and 3. Another you may see otherwise 3 in boys, 4 in females. Now how to believe that the results which we have seen are actually due to chance, or there is some other explanation? And the whole idea of doing this exercise, doing this interaction today, is to quantify the chance. And that is what we are going to do. So initially what we'll do, we'll go again with the steps. We assume that the null hypothesis is correct. That means there should be equal number of males and equal number of females. The probability of an intestinal perforation should be equal. That means it should be 0.5 in case of male and 0.5 in case of female. 0.5 means 50%, right? Since there are only 2 options. So let us see. Let us do a little bit of calculations. Don't worry, I'm not a statistician. I don't know much mathematics. I just made a very simple mathematics for you. And I know you would be able to see that. Okay, let's see. You have 7 of them are males. You just see that all 7 who suffered from intestinal perforation were males. So let's calculate the probability. And probability we would be able to calculate by. Are you able to see my whole slide? No. Hello?
No, so there's this orange thing that's covering
Yeah,
up
I think
the.
that's a little problematic. I'll take care of something. So what I've written is if all were males, that intestinal complication happens in all males. Mean male, 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 male. Right? No, since these are independent events. If one male gets into intestinal perforation, it doesn't make the second male more or less susceptible to intestinal complication. So once we do that, we have to multiply these probabilities. So what we do is 0.5 into 0.1, 1 by 2 is 0.5. 1 by 2, 1 by 2, 1 by 2, 1 by 2 would become 1 by 128. And when you multiply it, it would become 0.007. No, what does this mean? I'll come later. So just remember, it is something like 0.008. Now let's say that there are, I'll explain it here, that there are 6 boys and 1 girl. The probability of 6 boys would be how much? 7 by 128. 6 boys and 1. Look at this. 6, 1, 6, 1. I'll make it little better here. So, what is the probability of the 7 cases being 6 males and 1 female? You have to multiply that. 1 by 2, 1 by 2, 1 by 2, 1 by 2, 1 by 2 is 7 by 128. Okay. What is the p-value of 6:1? P-value of all 7 would be 0.008. Right? P-value of 6 and 1. Which way? You can think 6 males, 1 female, 6 male, 1 female. It could happen like that also. Would be like this. 1 by, this is all boys and no girl. This is all female and no boy. Again, 6 male and 1 female and 6 female and 1 male. We have to sum up all these. So what we do is 1 by 28 is this one. You have 7 by 128 is this one. You have 7 by 128 is on the other extreme, and 1 by 28 has 70. This is 7 females. Now I'll again repeat what we said in the p-value. And what we said is that you accept the null hypothesis. Now why this has happened? Let me go it. Where it is, sorry. So I said p-value is the probability of observing as extreme a result as extreme or more extreme. So what is more extreme than 6:1? 7. But it could have happened both ways. It could be 7 males or 7 females. And what is the probability of 1:6? Again, it is both ways. So it is either as extreme we said 6 boys and 1 female. And more extreme would be 7 and 0. So we would sum of these probabilities and then we come up with something like this. The probability when we calculate is 0.125. Now, 0.125 comes where? Let me go. Sorry. 0.125 comes where? Let us come here. Yeah. This is 0.025. 0.125 comes between these two, close to the center line. So close to the center line, what decision you would take? What decision we are going to take?
Accept the null hypothesis.
Accept the null hypothesis. You got my point? Had it been beyond 0.25 in any direction, what you should have decided, concluded, you would have rejected the null hypothesis and accepted the alternate. You would have said that this seems to be a difference which cannot be explained by chance. There are some other factors. Other factors would be, it could also be a real difference. I hope you understand with this example what is level of confidence and how you calculate P and make a decision in that, right? But this is not enough. This is not enough because you have to do a little more. And little more would be like this. I think I have done this. I've done with all kind of 7 cases male and 4, 3. I've given that in my figure. Now, let me go here. Yeah. This is again, it says, once you are in between the two lower lines, vertical lines, you accept the null hypothesis. Once you are beyond that, your p-value goes in the tails, then you reject the null hypothesis and accept the alternative. Okay. Now, you can make 2 decisions. You can make 2 right decisions and you could make 2 wrong decisions. You have collected the data. You advocated some level of confidence to start with. You collected data, collected observation. You applied some test of significance. You generated a p-value. And on the basis of whether the p-value was beyond that significance level, you rejected the null hypothesis. Otherwise, you accepted the alternative hypothesis. Now, sometimes it so happens that you could make 2 wrong decisions and you could make 2 right decisions. And these are known by fancy names, which is called as type 1 error and type 2 error. If you just remember, reject the null hypothesis when it is true, then it's an alpha error. I think my slide has there's a problem with the slide. True should come and in place of false. So there is a problem of alignment. Accept the null hypothesis when it is false. Then it is called as a type 2 error. So you are making 2 correct decisions. There was a difference and you said there is a difference. You made a correct decision. There was no difference and you said there is no difference. You also made a correct difference. Now the problem is, which one of them is a bigger bigger error to make? Is it saying that there is a difference when there was not? Or there is no difference when there is? Both has implications. Let me say you have a disease for which you do not have any known treatment. So what you would do, you would be happy to even make a bigger error, type 1 error, in accepting something as useful when in fact it is not, because you do not have anything to rely upon. But when you have a plethora of drugs already there, which are very effective, and you're looking at some other extraneous thing, whether it has lesser side effects or it is more cost effective, then you would like to have a more confidence in that, and you would actually go for lessening the type 2 error. So it's an interplay, it's a trade-off And it is the clinician who has to decide which one he or she would tolerate in a particular setting. Type 1, generally, we say it's 1 minus 0.05. Your level of confidence is 0.05. So 1 minus 0.05 is called as 95%. So you are billing, as I said, you are willing to take 0.05 error, 1 in 20 times of making a wrong decision, saying, concluding that there is a difference when there was not. That is the convention level. And the convention level of beta is 80 or 90. That is, you start with that. You say that I'll take 1 in 5 or 1 in 10 times error to say there was a difference, but I said it is not, because you already have some drugs with you who could do the job for you. Okay? I hope the concept is clear. Once you have collected the data, you'll make as a clinician has to make a decision. And two of your decisions could be right, and 2 of your decisions could be wrong, right? And the one kind of decision which is called as alpha error is, as I would say, is little more problematic for investigators. Similarly to what we do in our legal practice. You say that no innocent should be convicted, even if many guilty are set free. And that's the same kind of reasoning which we use. And it is not only in experiments that we use this kind of reasoning. You make this kind of reasoning in what you call as in legal practice. You make this kind of reasoning in some other things. And this particular slide would show it would not matter if you set your type 1 and type 2 error quite arbitrarily. It's not going to make much of a difference if you are not willing to believe in God. All right. Okay, I'm sorry. This is about, I said, I'll tell you a fable. It is called The Boy Who... I'll make this particular presentation again, change it, and share it with you. Don't worry. Okay. The caption is The Boy Who Cried Wolf. We made both the wrong decisions in this situation, in this fable or in this particular story. When the boy cried, there was a wolf. People went there and saw no wolf. And then there was a time when actually the wolf came, but nobody came there. So one time we made type 1 error, and the other time we made type 2 error. So this kind of decision making is a part of everyday's life. Now we have done a little bit about how to calculate that p-value, how to make a decision, whether we make a right decision or a wrong decision. But this is not enough. Now, there has been many kind of debates about the use of p-value, and it is not new. Many statisticians of eminence, the first one was the Roland Fisher. He gave the concept of p-value. But many others, Pearson and Neiman, were not very comfortable with that. They said p-value actually doesn't tell us much about. It doesn't tell us about the clinical relevance or the importance of the observed treatment effects. Despite a significant p-value, it's quite possible for the differences between two groups to be small. And actually it happened in a landmark trial done by Austin Bradford Hill. You know, we still keep on trying vitamin C for common cold. More data has accumulated, but the landmark trial I'm trying to share with you was conducted in maybe in 50s. So he collected Austin Bradford Hill, the statistician, he collected two groups. To one he gave randomized. He gave vitamin C, to other he gave placebo. He collected data on a number of subjects, and what he found was that the p-value was 0.0001. 0.0001. That means the result of this particular magnitude could have been possible in less than 1 in 1,000 times. And said, we reject the null hypothesis and we say that vitamin C is better than placebo in common cold. But you know what conclusion he drew? He said, listen carefully. He said, if you take vitamin C, you get well in a week. If you take placebo, it takes 7 days. So there is no difference. There is no clinical relevance. Something has been shown to be highly significant, but it has no clinical significance. So you, me, and others, our job as clinician, as investigator, is to see whether something which we have observed, it may have been very, very highly clinically significant, statistically significant. It might have no value. And let me tell you, it says, if you have numbers, if you study something on thousands of people, you can virtually prove anything. Because if you have to prove a difference, statistical significance in small magnitude, let's say 0.01 and 0.02, which may not be clinically relevant, or a 2 millimeter mercury difference between drug A and drug B, which you know is of no clinical relevance to you. If you take large enough sample, then you prove it. That is why in statistics we say, torture the data till it confesses. So most people do what we call as a data dredging. So they collect data and they keep on applying multiple tests. And when you apply multiple tests, for one test, your level of significance is 0.05. If you apply 10 tests on the same data, your level of significance doesn't remain 0.05. It is 0.05, 0.05 into multiplied by 0.05, 10 times. It becomes 0.40. That means 1 into 2.5 times. 1 in 40 is 1 in 2.5 times. You could observe a difference of this magnitude just by chance. So virtually it is not an important difference. So you as an investigator has to decide. Statistics would offer you insight, but the decision making lies with the investigator, right? I hope I'm clear.
Yes, sir.
Do I need to explain something? What I'll do is I'll change the format of the slide again and share it with you. And if you have any questions, right, before I take the second class, you please give it to me so that I can focus on those slides. Okay?
Sure, sir.
Now,
Sure, sir.
we have started with what? We have started with significance testing. We did that tossing exercise. Then we went on to decide the confidence interval. Then we talked about p-value. Then we made some decision. And then said p is not enough. There has to be something more. And what is something more? Something more is confidence intervals. I hope you would have heard about what those confidence intervals are. When Dr. Bhavna would have talked about the normal distribution, she would have talked about standard deviation and standard error. So for something which you could quantitatively measure, जिसको आप जैसे कोलेस्ट्रॉल है, हीमोग्लोबिन 1AC है, जिसको आप मेजरमेंट कर सकते हो, तो कई बार आप उसका मीन निकालते हो, और आपने देखा होगा नॉर्मल डिस्ट्रीब्यूशन में मीन प्लस माइनस 2 स्टैंडर्ड डिविएशन contains how much percentage of observation? 95.45, right? So you could construct a 95% confidence interval and 99% confidence interval. And I'm sure Bhavna would have talked about the value which we use in normal distribution as Z for 95% is 1.96, and for Z 0.01 is 2.58. So once you make a confidence interval as 95%, you will have to multiply that standard error by 1.96. And if you're going to make it for 0.01, then you have to multiply by 2.58. So what you get? You get the thing like this. I'll show you. Now this is what you could see some bars. These are called as error bars. You could see there's a small, in the middle, there's a small little circle. This indicates the mean. And then you have a lower limit and you have an upper limit. And this is 95% confidence interval. Now, what does it actually mean? It says you have a population, like the population you had for typhoid and intestinal population. You had observed 6 and 1. But if you would have taken another sample from the same population, you might have observed 7 and 0. If you have taken another sample, you might have seen 3 and 4, or 4 and 3, or 0 and 6, multiple combinations. Similarly, when you measure something and you take multiple samples, and the idea is you do not actually do it in practice. You statistically do it that if I keep on taking multiple samples to estimate a particular mean in this population, what would be the spread of my means? So if you do 100 such different experiments, so you'll get a range which is a lower limit and which is the upper limit. And this is what is called as a confidence interval, and it offers you more insight than your p-value alone, right? Now let me come here. Now you have a table, and you could see this is the result of a trial, famous trial, which was conducted by Austin Bradford Hill for Medical Research Council UK. This is a reanalysis of that trial. At that point of time, there was no ARR or something. So what they observed, because streptomycin was scanty, it could not be given to everybody. So they said, let us run. It was the first of those randomized trials, and it's a wonderful trial. At some point of time, I would like to maybe talk about this trial. It's such a learning experience. So he randomized people with progressive tuberculosis, and we made a eligibility criteria that the streptomycin would only to be given to people who are 15 to 35. So he randomized them into either streptomycin group or bed rest group. And at that point of time, 40s, what was the treatment for tuberculosis? A collapse therapy, sending people to hill stations in sanatoria, giving bed rest, giving better nutrition. So in one group, it was bed rest, and in another group, it was streptomycin. And they looked at the survival at 6 months. So what they saw, that in the streptomycin group, among 55 people, 4 died. Whereas in bed rest group, 14 died. The difference there was 19.6%. Now, you have to decide, or you have to make figures really talk. You have to decide whether this 19.6% is good enough difference, is large enough difference to say that streptomycin should be given to everybody. Now, that's something you have to mention when you start a particular trial. Now, What I have done here is a little CI and error bars, and I said it is an inference by I. No, what you could infer by I. There are 6 bars. Look at the first 2 bars. Let's make a comparison between first bar and second bar. First bar and second bar, you see there's an overlap. You could see that in the confidence interval, there is overlap. First and
Yes,
second.
sir. Yes, sir.
Third and fourth, there is more overlap, isn't it? The mean seems to be the same. In the first one, the one mean is little higher, the other, there's a difference. In the second one, there is a less difference. In the third one, these 2 confidence intervals are apart. So what I want to teach you, a couple of lessons. Whenever you read a journal article, please look at the confidence interval. If you could draw that confidence interval graphically, and if you find a situation like a difference in E and F, where there is no overlap between E and F, the means are entirely different. The lower limit of the upper bar doesn't in any way overlap with the upper limit of the lower bar. Without applying any test, you could conclude that there is a statistical difference. Now, what would be the magnitude of that P? Would it be 0.05 or 0.01? That is something which is, but you could definitely, if you apply a particular test like a chi-square or a t-test, depending upon what kind of observation you have, you could simply be verified by applying that test and say that the results were statistically significant. In C and D, you can simply say there is no difference at all. If there is something where there's a gross overlap between C and D, and the means are quite close to each other, you could simply conclude that the differences are not statistically significant. It is only in case of A and B that making decision influenced by I becomes a little difficult. Here, you'll have to go and apply a test of significance, whether it's t-test or chi-square test, to make a definitive conclusion. So I hope you got it. I said confidence interval is much better. And look at this. Wherever you see the confidence interval as a very long one, that indicates one thing, that the sample size might have been small. If you look at the length of the limbs as small, you probably are dealing with adequate sample size. These are the kind of things, and these are the kind of inferences you could make while you read papers, and this is what a competency you want to learn today, right? Now, let me give you, now this is the same which I said. If you have a 20 number, you are the first one. If you are doing something on 20 people, the length is like this. Whereas if you are doing something on 5,000 people, your confidence in your finding is very, very high. Your range is very low. You say with certainty that your estimate lies between a very narrow range and you're pretty confident. Whereas if you're doing it very small number, let's say 20 people, you say that my estimates are quite imprecise. They vary too much. And finally, I think I'll give you something to do at your home. Now, if the surgeon's wife was only interested in physician's prowess at tossing tails, after how many tosses would she persuaded her husband to stop at 0.05 and 0.01 level of confidence? Do it at your home and share the results with me, and we'll talk further, right? Now, what I'm sorry, because Once I transmitted my presentation from my laptop to the iPad, there is some problem in the alignment. What I'll do is I'll make it simple and share it with you people. You study it again, and if you have any queries, I think we can take it next time. Right? Thank you very much. Any questions? I'm here to answer all those.
Okay. Thank you so much for the session, sir. We are now opening the floor for questions. If anybody
Yeah.
has any questions, please feel free to share them either in the WhatsApp group or in the Zoom meeting chat box, or you can raise your hands.
It would be wonderful if you just speak up. I think everybody would get benefited. And that is what you should be doing. You are young, and if you don't ask questions, they say if everybody in the room is on the same page, feels the same thing, it means nobody has learned anything. So there has to be some questions. There has to be some queries. And inquisitiveness is the mother of all discoveries. You must, it may be bad question, it may be wrong question, doesn't matter. But you must ask questions, right? Please.
Do
Sir,
we have
I have
any
this query.
queries?
Yeah,
I have
please tell your name and please. Yeah.
So my name is Aradhya.
Aradhya, batao bete.
Yeah, I have this query ki, like you said, that we could use the confidence interval as well as the p-value to determine whether the results are significant or not.
Yeah.
So, like you also said, sir, that confidence interval is a better tool to predict the same results.
Yeah, absolutely.
So, sir, how would one determine like the same results with the p-value?
See, what has happened that in the evolution of statistical testing, it was a
Yes.
p-value which was suggested earlier on,
Okay, sir.
maybe 50 years, 70 years earlier. 1930s it was, I suppose, right?
Right.
And there was some problem with the p-value. Because p-values, you could see that it is very arbitrary, right? You don't get the magnitude of the difference. See, what you want to do as an investigator is to quantify the difference. One, you want to see whether the difference is small or big, and then you want to decide whether this size of this magnitude of difference could happen by chance or not. Right? This is what we are supposed to decide about. P-value does give you a quantification of whether it has happened by chance or not. But it doesn't lead you to other things. A confidence interval, if you look at the two limbs, you get to get the range. You say that, had I been doing this experiment over and over again, this is where my mean should have been 95% of the time. In both cases, in E and F or in C and D. So that offers you more confidence in your finding. And I said, you do it whenever you get time, you do it on your own. If you have a situation like E and F, let me give you that it is going to be statistically significant. The idea is people have advocated that you should also tell us p-value, and that's possible by the use of statistical software also. And that I think we're going to do next time. So what
Sir,
I will suggest is, if you have to do a study on your, no, I would suggest applying the CI first. And with the help of statistical software, you could calculate and you could write the p-value as well. You got my point?
that was my only question. Like, is it mandatory that we need to mention the p-value as well? If
Yeah. You have to.
Okay.
See, what I'm telling you is, जब आप पहले इनिशियल अपने डेटा देखते हो ना, जब शुरुआत में हम डेटा देखते हैं, तो डेटा शुरुआत में जब हम करते हैं तो वी गो स्टेप बाय स्टेप. We don't go into advanced analysis. I would tell all my students all over in 30 years, I said, if you do not describe your data well, you do not do analysis of the data well. तो हमें प्रॉब्लम क्या है? हम सोचते हैं कि जो descriptive statistics is useless. It has no value. What I tell you, most of your questions which you want to answer actually come from your description of what you have seen. And when I say it's influenced by I, if you make a diagram like this, before you apply a formal test of significance, you are already there. You see? And many times when you're doing a trial, and if you are allowed to do a midterm analysis, and if you are able to see such kind of a diagram, you could simply stop the trial. You say, I've got the evidence. There's no further use of going for the trial. There's some trial which is called as a sequential trials, where you are allowed to see the results at multiple times, where you are bothered whether the treatment which is new might give rise to some very, very adverse events, right? So this is a kind of a descriptive strategy. Apart from being a descriptive strategy, CI also offers you many initiatives, avenues for what we call as the analytic testing. So I would suggest that you say CI and you give P and your work is done. You don't give P value, doesn't matter at all. You got my point?
Yes, sir. Thank you so much.
Thank you. Yes?
So, do we have any more queries?
Simran has raised her hand.
Please, Simran.
Simran raised her hand previously, but now her hand is not raised.
Dipali,
Simran, do you have a question? Simran, do you have a query?
Yes, sir. Hello, good evening, sir.
Yeah, good evening. Simran?
Like, does size of data has effect on p-value?
Pardon?
Size of data has any effect on p-value?
Size of data, I said, if you have a sample size which is very extreme, right?
Sure.
The p-value, you could prove anything by p-value. I give you one example. We were a part of one particular trial, which is a crash trial, which is a clinical randomization of antifibrinolytic in significant hemorrhage. And the outcome which we were likely to see was a 2% decrease in mortality. And 2% was from 18 to 16. 2% could be from 4 to 2. 2% could be from 18 to 16. 2% could be from 44 to 42. Each one of these situations are different. From 4 to 2 it becomes a 50%. From 18 to 16 becomes very less. So if your size of difference which you are looking at is small, you would require mammoth numbers. Do you know how much sample size was for this trial to detect a 2% difference? 22,000. 11,000 in one group. To detect a difference of 2% in patient who would come with a trauma, multiple trauma, and if they are given tranexamic acid, they would not bleed further or they would not die. No, this is a very small difference. And to detect a difference of this size, you require a sample size of 22,000. Now, here comes the question of who decided this? Whether this difference was 2% was enough to merit clinical significance. You know how many people met with accidents and trauma? Millions of people, right? So even if you cut down on the mortality as 2%, you are still going to save thousands of lives. So that becomes your clinically significant difference. You got my point? If you have to see a big difference, you would require very less numbers. So if you are looking for a difference, and then of course, when you decide on a particular experiment or a trial, that is why we say that you have to do enough review of literature to find out what is happening on the ground. How much difference would you be able to produce with the new drug? On the basis of that, you before and tell, this is the effect size, the difference I'm going to look at. And if the difference you're going to look at is very small, then I'm afraid you are going to be looking at large numbers. But if you have large numbers as such, and you apply any sort of test, I'm sure, as I said earlier, you'll get many tests as positive, whether they are clinically relevant or not. I hope I answered your question, Simran. Simran,
yes,
ठीक है?
yes, sir. Thank you.
Any more questions?
So there are no more questions. Are there any more questions?
Guys, if you have any queries, you can raise your hand or put it in the chat box too, if you're not willing to unmute yourself.
Another what I will suggest is, even if some people are hesitating, I would be available on my WhatsApp group. You keep on putting those questions till we have the next class, so
Sure,
that
sir. I
even
guess we have a
something
question.
which has not been taken care of in this class will be taken care of in the next class.
Sure, sir. But I guess we have a question. Rakshit Goyal has raised his hand.
Yeah,
Rakshit,
please,
I'll ask you to unmute
go ahead, go ahead.
Rakshit, you can go ahead with your question.
Very good evening, sir. This is
Good
Rakshit
evening.
Goyal from Thompson Hospital, final year. This was a great lecture, sir. Thank you so much, first of all.
Thank you.
Sir, I wanted to ask you that if we are studying a disease, like some disease, any disease, and I have to study the advocacy of a drug, A and B for that drug.
Mhm.
So if we have to check the significance to the confidence interval, I need a second study too, isn't it?
You need what?
Sir, if I'm studying about a disease and I have to study the advocacy of drug, for example, A and B for that particular disease.
Okay.
So I want to check its significance to the confidence interval. So I would need a second study for this too.
But if I could understand your question, you said you are going to do a fresh experiment, isn't it? Or
Yes,
you are
sir.
going to review the literature.
Right, exactly.
Or you are going to review the literature.
Sir, I'm asking you if I have to study about the advocacy of drug A and B, like there are two drugs for a disease, like A and B. So I have to check out their significance for the confidence interval. So I'm already conducting a first research. So I would have to already have a second. I should have a second research about the another drug too. So how could I
This
compare
is,
it?
I think, a
study
very,
that?
very wonderful question, Rakshit, but it is quite complicated. Let me tell you one thing.
Okay, sir.
They say, if you already have evidence of some kind, which is proven by the gold standard, which is randomized controlled trial, right? There should be no need to go for any other, no need to go for replication, right? If you have a RCT, which gives you the evidence, strong evidence, or you have a meta-analysis, which gives you, which is a combination of studies, then you should not actually plan another trial. There is a term which is called as a clinical equipoise. Clinical equipoise. EQUIPOISE. My pen is not working. Equipoise is
clinical equipoise.
Equipoise. EQUIPOISE. Right?
Okay, sir.
Now, what does that say? It says you do trial only when you can't decide whether A is better than B or B is better than A. If you already have that evidence in literature by way of a randomized control trial, which is considered as a gold standard, or a meta-analysis, all right, then doing such trial would be unethical. You got my point? It would just be a waste of resources. So you go back to the review of literature. If you find such trial which gives you, for example, if I say, no, we have done this particular trial which is at tranexamic acid in patient with trauma. Somebody else says, no, I'm going to do it further. It would not be fruitful to put your resources on 22,000 people again, just to replicate that finding. What you could do is, on the other hand, if you have some element of doubt, you look at all kind of studies which has used tranexamic acid and placebo, combine it together, get a combined estimate, and that is what is termed as a meta-analysis. I hope I answered your question.
Yes, sir. It was great, sir. Thank you so much. I have been so lucky to attend this lecture. Thank you
Thank you
so much.
Rashid.
Any more queries? Sir, I think we are done with all the queries. Yes.
Thank you, Arya, and thank you, Aradhya, and thank you everyone who joined. And I once again apologize. I was not, because I don't use iPad normally. So what happened, I thought it would be better to write something on that, because I'm right now in Jaipur. So my other laptop is actually at Jammu, which is a touch where I can write. And so I was not, I couldn't see properly whether there's a proper alignment of the slides or not. But I think it did not do any harm. So what I'll do, I'll again share the same slide after changing the format. And whatever questions you have, I would be very happy to answer next time or in between the next lecture. It was, I must congratulate you, all people. When I got a call from Bhavna, I was actually very, very happy. Because whatever I have taught people on research methodology, शुरुआत में ऐसा लगता था कि मैं खुद ही जाता था, खुद ही पढ़ के आ जाता था. Things are so bad. I read it in one particular book. It says, जो statistics हम पढ़ाते हैं ना, मैं पढ़ाता हूँ, मैं तो या कोई और पढ़ाते हैं, particularly biostatistician, they teach statistics akin to a method, similar to a method. They say learning to swim by drowning method. अगर आप किसी को धक्का मार के स्विमिंग सिखाओगे ना, तो जिंदगी और पानी के पास नहीं जाएगा. This I understood many years later, कि जितने लोगों को मैं शुरुआत में स्टैटिस्टिक्स पढ़ाने की कोशिश कर रहा था, सबको धक्का मार रहा था. Till the time I could understand कि जितने लेक्चर में दे के आता हूं लोगों को, वो खुद ही समझता हूं, दूसरा कोई नहीं समझता. No, why I am happy? I am telling you. I did not tell you the reason. The moment Bhavna shared it with me that there is a motivated bunch of 100 people, maybe more than that, who are taking these classes voluntarily. मुझे लगा जो 30 साल का मैंने कुछ कहीं थोड़ा मेहनत की थी ना, वो कहीं ना कहीं रंग ला रही है. I know what your option would be. Many of you would be going to do USMLE or PLAB or something where these things would be of quite handy. But nonetheless, every practitioner has to be a good researcher. And to do good research, the first thing is to understand research. Doing research is a secondary outcome of understanding research. If you understand it well, I don't think you would require. See, for investigators and clinicians, it is not the fancy statistics जो आपको चाहिए. आज तो आप कुछ भी निकाल लोगे. What you should be able to understand is to interpret what output has come out of software. उसके लिए क्या जरूरी है? उसके लिए जरूरी है आपको understand करना. Your work is observation and generation of clinical ideas. बाकी सब कुछ हो जाता है. The biggest problem is how to generate those research questions and such ideas. And that comes with observation. And this observation sharpens once you are through with the concepts where you could understand two things. One is the statistical method, and second thing is epidemiology. Once you're through with it, elementary course, I think nobody can stop you from doing a wonderful work in years to come. And I wish you all the luck, and I congratulate every one of you for such an initiative. And I would be available for you anytime you desire. Thank you very much.
Thank you so much, sir. Thank you so much for your wonderful insight, sir. And thank you everyone for participating actively. Sir, we'll be ending the session now. We'll be wrapping up the session. You can leave now.
Thank you.
We'll monitor the attendance. Thank you so much, sir.
Oh.
Okay. So the feedback form has been shared in the Zoom meeting chat box. You can start filling it, and you can leave as soon as you fill it so that we know that you've marked your attendance. Thank you so much for joining, and we hope to see you again for the next session next week. And it will also be taken by Dr. Dinesh Kumar.